The talk about Coriolis flow meter, which we didn't finish last lecture. So the flow meters will be all covered, and then we'll do the topic for today, which is liquid level sensors. I think that we will be able to finish it today, so this will be our last lecture for this semester. So on the last lecture, we have discussed Coriolis flow meter, flow meters in general, and I've discussed ultrasonic, electromagnetic, and orifice plate, and the last type that we didn't have time to cover is the Coriolis flow meter. The Coriolis flow meter is quite different from all the other three flow meters that we have discussed, and the difference is that the Coriolis flow meter measures directly mass flow. The three previous types have measured volume flow or speed, and then this was multiplied by the cross-section. But Coriolis flow meter measures directly the flow. The Coriolis flow meter takes use of the Coriolis force that is created when you have a moving object and you have a motion that is implied to this object, for example, vibrations or rotational movement. So maybe before we go to that, to some details, let's take a look on a simple experiment. Imagine that you have a tube with water, for example, and the tube is filled with water, but the water is not flowing. And you impose vibration on the tube. So you make the tube move back and forward like this with some external actuator, and you are watching what the tube is doing. So when there is no flow, you see that there is a uniform oscillation of the tube. But as you start the water flow, then the movement will change. The change is due to the Coriolis force, and you can imagine this as an inertial force that is here at this part of the tube. The flow is from left to the right, so the water, the liquid, is flowing from left to the right into the tube. And we are making this tube oscillate. So we are implying the motion, let's say W. It could be also an angular motion, a rotation, for example. And at this moment, you will have a Coriolis force that will act in this direction, and this Coriolis force will be proportional to the speed of flow and to the angular velocity. On this end and on this end, the angular velocity, omega, is going into opposite directions. So you will have a Coriolis force here going downwards and a Coriolis force here going upwards. So this will cause you this, let's say, twisting of the tube. And if you will be able to detect the instantaneous position of the tube at this position and at this position, you will have a Coriolis-based flow meter. What you see here on the pictures is a version when you have two tubes, but it can be done also with one tube only. So the basic operations that we need to do in order to create this flow meter is that we need to imply some motion, and that we need to be able to measure the position of the tube. So the construction of the Coriolis flow meter is the following. Here you have a driving unit, eventually driving coils. So it's the actuator that makes this tube move up and down. So you're making the tube move. The tube is twisted like this, and here and here you see we have displacement sensors. Those sensors can be, for example, inductive sensors, so they are detecting the motion of the tube up and down with good accuracy. So when there is no flow, the tube will oscillate back and forth uniformly, and the oscillations will happen at the same time at this position and at this position. So when you look at the signals from those sensors, it will be some form of sinusoidal signal, but there will be no phase shift. Since you applied flow, then the movement will continue, but there will be a phase shift between this position and between this position, and this phase shift will be proportional to flow. We'll take a look on a very interesting video where they show how this works internally, and you will see also some industrial sensors in this video. So first I have to launch it. Hopefully the internet will be working. Oh, some problem. Again, some black window only. For some reason I cannot open the internet with the video, so I'll try again later. Let's take a look on the properties of the flow meter. Okay, now there's some problem with the computer. Okay, it's crashed. Fine, so let me just restart my computer. Before this happens, so what are the properties of the Coriolis flow meter? It measures directly the mass flow. So you have a different principle that measures something else than the other sensors. Of course, you can recalculate between mass flow and volume flow if you know density. On the other hand, the Coriolis flow meter allows you also to measure density independently. Because if you have this shape of tube, so looks like this, then we have this driving mass here and the position sensor is here and here. Then the signal that we will see from those sensors, this is time and this is some amplitude of the motion. So then when there is no flow, you will have zero phase shift. So we will see two signals. But you can measure also independently the density of the liquid that is inside the tube. Simply because the resonance frequency of this mechanical part will be a function of the density. So the density, or mass, better say mass, of the assembly, but the mass of the assembly will have two parts, the mass of the tube plus the mass of the liquid that is inside. And when this will be changing, you will see a change in resonance frequency. So by looking on the phase shift of those two signals, you can measure flow, and by looking on the frequency of those signals, you can measure density. So the Coriolis flow meter allows us to independently measure the density and flow at the same time. I hope I will be able to launch the video now. Yeah, now it seems to work. Okay, so let's take a look on the video about Coriolis flow meters. You will see some applications as well.
Most diverse substances are transported and distributed in pipelines every single day. This may include drinking water, fruit juices, oil and gas, as well as chemicals, acids, or alkalis. The fluids flowing through pipelines often display completely different properties. Consequently, there are different principles for their measurement. One such method is flow measurement based on the Coriolis principle. The French physicist Gaspard Gustave de Coriolis set out the physical basis for this measuring principle over 200 years ago. What is interesting is that the Coriolis principle allows the flow of mass to be directly measured. Let's take a closer look at how this measurement method works. A tube is located inside each Coriolis flow meter. An exciter causes this tube to oscillate constantly, here in an exaggerated example. If there is no flow, the measuring tube oscillates uniformly. Sensors are located at the inlet and outlet and register this basic oscillation precisely. As soon as the fluid starts to flow in the measuring tube, however, additional twisting is imposed on the oscillation as a result of the liquid's inertia. Now, due to the Coriolis effect, the inlet and outlet sections of the tube oscillate in different directions at the same time. The highly sensitive sensors pick up this change in the tube oscillation in terms of time and space. This is known as the phase shift and is a direct measure of how much liquid or gas is currently flowing through the pipe. The higher the flow velocity, and thus the total flow, the greater the deflection of the oscillating measuring tube. The application of the Coriolis measuring principle doesn't stop here. It can also be used to simultaneously determine the density of the flowing fluid. To do so, the sensors also register the oscillating frequency. In other words, how often the measuring tube moves back and forth in 1 second. From the animation, it's clear that a tube filled with water oscillates more frequently than a tube filled with honey, for example, which has a far higher density. Thus, the oscillating frequency is a direct measure of the fluid's density. Both the density and the flow are determined simultaneously, but independently, via the tube oscillation. Endres and Hauser has continuously revolutionized and perfected Coriolis flow measuring technology in numerous innovative systems. This measuring technology is unique, as it's the only way multiple process variables such as mass flow, volume flow, density, temperature, and even viscosity can be measured simultaneously in pipelines.
Okay, so now let's take a look on the properties of the Coriolis flow meter. So let's just open the presentation. So we'll compare the Coriolis flow meter with the other sensors in terms of installation, in terms of range, for example, and what can it actually measure. We'll see also some internal pictures of the Coriolis flow meter. It takes a while before it starts. So inside of a Coriolis flow meter, we have the tube, which you have seen on the video, and therefore the Coriolis flow meter has a typical shape that you see directly from the outside. It is this shape that is hiding the tube. Then we have the oscillation system, which is here in the middle. It can be, for example, electromagnetic, and then we have two pairs of sensors that measure the position, as we have seen on the video. And then the electronics is hidden in this case and sends a standard signal. So the Coriolis flow meter is installed inside the pipe system with a flange. It's not possible to mount it outside like the ultrasonic flow meter, for example. Here you have an example with the two tubes. The two tubes can improve the response of the sensor because they are able to suppress external vibrations. You are looking for the movement of the tubes against each other, and this will suppress any external vibration. So it can measure more accurately when you have external vibrations. The tubes that are used are either from steel or from other materials, so typically metal. And here we have an example. A stainless steel tube is typically bended. If it operates for higher temperatures, you need to make the tube from a different material like titanium, for example, which will be more expensive. Here is the explanation why we can measure density as well. So it's shown on the example of two tubes. So the two tubes are vibrating against each other. We're measuring the displacement, and on the signal we see some resonance. So we try to operate this on a mechanical resonance, and the resonance frequency of this assembly is influenced by the density of the liquid, because the resonance frequency is changing with the weight of the assembly. So here you have a formula that allows you to calculate the weight, and here you see that this mass of the fluid depends on the volume and on the density, so it will change the resonance frequency. At the same time, while looking on the phase shift of the signal, we can independently get the information about the flow rate. So what are the advantages of a dual or a single tube Coriolis flow meter? The dual flow meter is internally balanced, so it allows you to suppress external vibrations. It may have larger pressure loss since you are using two tubes, but with a smaller diameter at the end, so this will give you a little bit larger loss. On the other hand, the single tube version has higher sensitivity to external vibrations, external disturbances, but it's using a larger tube, so that this has a smaller pressure loss. What are the advantages of a Coriolis flow meter? So it measures independently flow, density, and if you equip that with a temperature sensor, then temperature as well. A typical sensor is a PT1000 that is installed. It is highly accurate. The typical accuracy is about 0.1% of the range, so it's one of the most accurate sensors. It does not require any inlet and outlet distances. So it means that you can connect it directly in the piping system, and you don't need to have a straight section in front or behind the sensor. We have seen that this is a problem typically for the orifice plate, and the other sensors were progressively decreasing this necessary distance. So for the Coriolis flow meter, the necessary distance is 0. You don't need any inlet and outlet straight sections. And it can independently calculate the properties of the liquid, such as flow. If you know density, then for a single phase solution, you can calculate what is the concentration. For example, if it's a mixture of sugar in water, alcohol in water, and so forth. The Coriolis flow meter can measure for small flow rates. It can measure cryogenic liquids. We have seen that this is a problem for the electromagnetic flow meter, for example. The pipe diameters are up to, let's say, 0.5 meters roughly, so quite large pipes, but definitely not as large as the ultrasonic, where we had like 4 meters, for example. large pressures and temperatures up to roughly 350 centigrades. And the last disadvantage is, now the title is wrong, it should be Coriolis flow meter. It has a higher pressure loss if you compare it to ultrasound and electromagnetic, because ultrasound has zero pressure loss. It performs best if you have a single phase liquid, so a mixture of just two components, and it's quite expensive. So it is one of the most expensive but most accurate sensors that you can have for flow. Here are some pictures of installations. So you see the typical shape. This cover hides the bended tube so that we are able to measure the Coriolis force inside. And from the picture that will follow, we will learn that the flow rate will be from bottom to top, since this needs to be filled again at all times. So here from those pictures you can say, okay, the liquid is pumped from the bottom to the top like this through the flow meter. So how to install the Coriolis flow meter? You should install it in such a way that it remains full at all times. You see, this is an example of a horizontal installation, and this is not suitable for liquids with solids inside. So if you have this example, then this is not an ideal position, because the solids will be accumulated here at the bottom position, and they can remain in this position. So the horizontal installation is only for clean liquids that do not have any solids in them. On the other hand, if you have a fluid with bubbles or gases, then this is not a good idea again, because the bubbles will accumulate on top of here, and there is no way to drain them, to remove them from the flow meter. So the horizontal installation is not ideal, and the Coriolis flow meter should be installed in a vertical installation, and it should be installed in this position. So the flow is from bottom to top. In this case, the eventual particles will assemble somewhere on the bottom and will not remain in the sensor. If there are eventually some gases, bubbles, then they will go through the sensor and assemble somewhere on the top, and you have an ideal installation. You should not do this. You see here the sensor is installed on top of the piping system, so then all the bubbles assemble at this position, so that's not correct. And the same problem is if you install the sensor when the flow is from top to bottom, then you are not sure that this is full at all times, and it's again a problem. Any questions? Okay, no questions. So now I promised you that we'll do the Moodle test for flow today. So now we'll do the Moodle test, and then I'll keep on with liquid level. Okay, so let me start the Moodle test. It will be the Moodle test for lecture 12, I think. Let me verify this. Yes, bonus test 11 done on 12th lecture. So the session is started, you can log in. No, bonus test 11 done on 12th lecture. That was supposed to be last week, but we didn't complete this Coriolis flow meter. So are you ready? I'm not yet. Okay, so let me know. Okay, so I'm starting the quiz. There are 4 questions as usual. Okay, so the ultrasonic flow meter, the clamp-on version, has no pressure loss. So the answer is true. You clamp it from the outside and you don't install anything. I'm sorry, we didn't. We will cover this today. 26 gigahertz is the correct answer. 26 gigahertz. For some reason, I added the question from this week. I don't know why. So select 26 gigahertz. It's a bonus for those who are actually on the lecture, because I see that there are 12 people registered for this test right now, and I don't count 12 people. Yeah, so fine. So yeah, it's fine. So 26. Okay, let me launch another question. Okay, I see 9 and there are 12 here. And the same problem here. Yeah. The answer is false. The liquid level meter based on conductivity requires a conductive liquid. So it cannot work with a non-conductive liquid. Okay, and I hope that the last question will be related to flow. Now, again, the answer is false. Yeah, the ultrasonic liquid level meter does not measure the amplitude, it measures the time of reflection. You don't have the question? That's strange. Okay, what does it say?
Feedback for your question. Please wait for the instructor to start the next question.
Really? All of you?
No, I did.
You had... Try to reload the page. Yeah, if you reload the page, it should update itself. It's false, yes. In the presentation. So, yes. Okay, so let me start with liquid level. I think we'll be able to finish it today. So liquid level sensors are quite similar to position sensors because we will see many similar principles that are used in position sensors. But liquid level sensing is specific in that sense that we may have continuous sensors and we may have point level detection. This is very similar to position sensors where we had continuous sensors and proximity sensors. The applications are different. You can require in the process that you have a continuous information about the liquid level in the tank, for example. But for many processes, it's also sufficient to have just information the tank is full or the tank is empty. So this is the difference between continuous and point level sensors. You will see that they can use similar principles for detection. So here you have a picture that divides these liquid level sensors into two groups. Here we have point level detection. So typically those sensors are cheaper than the continuous sensors which you have here on the right. And you can have different principles and sensors for solids and for liquids. So here, for example, you see liquid can use capacitive sensing, solids can use it as well. Continuous measurements could also use capacitive, for example, but most often it's using ultrasonic or hydrostatic principle. And for solids, we will discuss only ultrasonic, but here we have a radar as well. It's possible, but it's also very expensive. We will discuss only the principles that are highlighted in yellow here. So we'll discuss only capacitive sensors, ultrasonic, and then the hydrostatic principle. What is the problem in measuring liquid level? Imagine we have a tank like this, and it can be a storage tank for some chemical materials, for example. Here you have multiple options how you can install the liquid level sensor. So what you see here on the right are the point level sensors. We will be talking only about the vibrating fork. So here typically from the sides you install the point level sensor. So this detects you if the tank is full or if it's open. Typically from the top you install the continuous sensors. Here we have ultrasonic sensor, radar sensor, and the other sensors are quite similar. We'll discuss only ultrasonic sensor, and it measures the distance between the liquid level and between the tank. So what's the problem? The first problem is that typically you need some mixing in the tank. So if you have a tank when the liquid is steady, then there is no problem at all. You can simply measure the distance between the top of the tank and the liquid level, and that's it. It's quite easy. But what if you need to mix the liquid? For example, if you want to keep a uniform temperature, or if you want to prevent it from hardening, for example, then you have a mixer inside, and then where is the liquid level that you should measure? So should you measure here? Okay, the liquid level that you measure will be lower than the actual. If you measure here on top, then the liquid level will be higher. So what you are actually doing is that you try to estimate where the liquid level would be without the mixing. And this could be a problem. If we look a little bit more what can happen in the process. So we can have a liquid, and when this is just a liquid without any mixing, then no problem at all. But we can add bubbles. it can be a mixture of water and carbon dioxide, for example. So we will have bubbles, and those bubbles can prevent some sensors to work. For example, if we would install an ultrasonic sensor from the bottom here, then we will not have a clear reflection from the liquid level, but this ultrasonic signal will be blocked. So bubbles can be a problem. What if we add foam on top of it? We have a liquid, and there is a foam. For example, it could be a tank where you manufacture beer, and here you have a foam on top, and in this instant you cannot use ultrasonic sensor. It will be working from the top because the foam will absorb all the ultrasonic reflection, and you will not see the actual liquid level. You will either see nothing, or you will see the reflection from the interface between the foam and the air, for example. We can add vapors. So vapors can be aggressive, can destroy the sensor. We can eventually add sediments on the bottom of the tank, so this will prevent installation of the sensor from the bottom. We can add high temperatures, we can add high pressures, we can add acid or alkalis, we can add radioactivity, for example, and you may end up with something that is not possible to do with current technology. So we will see that it seems very easy to measure a liquid level, but if you have all this combined and you want that the sensor works for the next 50 years, then it may be impossible to do. So that's the problem with maintenance. You need to replace the sensor from time to time and maintain it. So this is related to liquids. What about solids? Well, in solids, what typically happens is that you have a silo with a solid. It can be sand, or it can be stones, or it can be grains, for example. And typically, you have some openings here. So as you fill the silo, then you don't have a uniform filling of this silo, and you have small holes. You may have multiple peaks, for example, here. So then if you look from the top with a distance sensor on this, then where should you measure? You should measure here on the peak, okay, then you estimate a liquid level, but then you miss this area when you don't have any material. So where is the liquid level? So you are trying to estimate what the liquid level would be if it would be filled ideally. And also, we may have mixtures. We may have a mixture of one liquid and another liquid. Typically, this could be, for example, a mixture of water and oil. The liquids do not mix together, but you have a liquid with lower density on top. Here, a higher density on the bottom, so this would be water, this would be oil. And you may have an emulsion layer, which you may also measure, and you may have foam on top of it. So this is typical, for example, in the petrochemical industry, when you pump oil mixed with water and you want to remove the oil from the water so that you can use it. So this is a brief summary. What technologies are available? We can measure with mechanical devices. It can be some float, it can be a lid that we just open and we look inside, see ourselves what is the liquid level. We can measure with capacitive changes or radio frequency signals. We will see ultrasonic in details. We can measure differential pressure, a radar, or laser or nuclear sensors. We'll not discuss this. What you see here is the price, of course, what is more expensive. And here you see what are the applications which are nearly impossible to measure. So if you have something very hot or very cold, if you have high pressures, if you have radioactivity, and so forth. Why is this important? Well, the reason is that you want to keep your recipe for your product to be correct. So, for example, you mix some components and you want to know that, okay, I should add 1 cube meter of this component, 1.5 cube meter of this component, and this will give me my final product. The problem is that when you store this in a large silo, or a large tank with a diameter, for example, 20 meters, that's nothing unusual, then even a very small error can give you a really large difference in volume that you are mixing. So here is just an example. Imagine we have a circular tank with diameter of 20 meters. We have the measurement error of about 10 millimeters, which is really large, and this will give us an error in a volume of 3 cube meters. So then either you sell 3 cube meters less or 3 cube meters more, but this could be a problem. So liquid level sensing requires typically a very high accuracy. If you are talking today about radar sensors, which are the most accurate ones, then the requirement is usually sub-millimeter accuracy. So you have resolution that is better than 1 millimeter. Let's start with the continuous sensors. So those sensors will be able to give us a continuous information about the liquid level. The basic principle is a hydrostatic sensor. So we know that the hydrostatic pressure in a liquid depends on the density, on gravitational force, and on the height of the column that is above this sensor. So if you install a pressure sensor on the bottom of an open tank, then you are able to measure liquid level. Simply, if you know the density, then you multiply that by gravitational force times the height, and you have pressure. So you read pressure on the pressure gauge, you know density. This implies that you need to know temperature, and of course you know the local gravitational force. What you see here on the picture is an example of a well-typed manometer, but you can use any kind of pressure gauge that we have already discussed. So you just install on the bottom the pressure sensor. The problem here might be if your liquid has sediments, then the sediments can block this opening. So this method is not suitable for liquids with sediments, since you need to measure always from the bottom. The other option is that you submerge the sensor from the top above some distance above the bottom of the tank, and you count this as an error in the measurement. You can measure with this principle also in pressurized tanks. Here we are looking for differential pressure. So this is an example of a U-tube manometer, just an example of a differential pressure sensor. And we have one pressure tab from the bottom, one pressure tab from the top, and then we are looking for the pressure difference, which is again proportional to the height of the liquid. Here is an example of a hydrostatic liquid level meter. Here is a diaphragm, and we transfer the motion of this diaphragm to this position sensor, which in this case is an LVDT position sensor. So we are basically sensing the deformation of this diaphragm with a normal position sensor. Here is another example. Those hydrostatic level meters are submerged from top on a rope or on a chain. So this is the probe itself. You submerge it all the way to the bottom of the tank, and then you measure the height of the column that is above this. So this liquid level meter is suitable for the applications where you either don't have sediments or you submerge the sensor from the top. It's not influenced by foams, because foams are on the top and we don't care about this. You can measure up to roughly 400 centigrades and up to roughly 400 bars. So foam is not a problem, and sediments are a problem in this case. The second sensor that I would like to show you is called a bubbler, and it is a very simple sensor that is, on the other hand, good for applications where you have sediments. The reason is that the sensor installation is done in such a way that it cleans automatically itself, and it is not affected by the sediment. The bubbler is in fact a pressure sensor, and we have a tank where we want to measure the height, and the only part that is in contact with the liquid itself is a tube. So this tube can be made from any material that is convenient. It can be from ceramics, it can be from stainless steel, it can be from plastic, whatever you want. And here we are blowing air into the tank. So we need a source of compressed gas, typically air. We blow this in the tank, and we have some bubbles. Now, the flow that you need to push the bubbles is proportional to the height of the liquid. So if your liquid level is higher, you will need higher pressure if you want to maintain the flow. So we have a flow sensor and we have a pressure sensor. The flow sensor can work together with the source of the compressed gas to provide a constant flow. So we are looking for a constant flow, and the pressure that we need to overcome the hydrostatic pressure will be a function of the liquid level. So we can have this flow sensor work together with a control system to maintain the constant flow, and then you have some flow that is constant, that is kept steady, and the output signal of this assembly will be the pressure that you have actually measured. So this is basically a pressure sensor. And the great advantage of this sensor is that the tube is the only thing that is in contact with the liquid. All this pressure sensor and flow sensor can be anywhere installed, and you can therefore work with aggressive liquids. You can work with acid, for example. The only problem here is that the liquid has to tolerate that you add some bubbles in there. So if you add this into an acid that you then fill and mix with other chemicals, then it's probably not a problem. If you would add this to a tank with beer, then this would be a problem. You just blow air and you are adding something. So you need to discuss this with the designer of this process and ask if this is possible or if it's not. Here is an example of such a system. So what you see here is the inlet port. So this is where the compressed air comes in. This is a pressure control station, so you can adjust the pressure in the system. This is a pressure sensor. So and you measure the pressure of the air, and here with this pipe, this would be connected to the actual tank, and this would function as the flow meter, at liquid level meter at the end. So this is a very simple system. You may have seen it in our lab 409. So it's just a tube that is in a tank, and it works very well. But as I said, the process has to accept that you blow the air. Also, you need this source of the compressed air, which can be quite expensive in time because you are blowing air at all times into the system, and this will cost a lot if you count that for the whole year, for example. Questions? Okay, fine. So let me go to capacity. This is also very common sensor for liquid level. We have seen a similar approach already for position sensor. The principle is that we are looking for the capacity of a capacitor, and either you have two planar electrodes, or you may have two circular electrodes. It doesn't matter. But the capacity that you measure is a function of material. It is a function of area between the electrodes, and it is a function of distance between the electrodes. You can change all three, but typically for liquid level sensing, you have the following arrangement. You have a tank. Somewhere in the tank, you install the electrode. And what you see here on the left is the case when the tank is conductive. So it's one electrode already, the tank, and you just put one electrode in the middle. So this can be either a rod, it could be a wire, it could be a chain, whatever you install, but it needs to be conductive since we want it to work as an electrode. So for non-conductive liquid, you are looking for the capacity between this electrode and the tank itself. We typically have three components. Component C0 is constant value. That's the electrode of the cable, of the connectors, of the assembly itself. So this is typically constant. Capacity C2 and C1, on the other hand, will change with the liquid level. Imagine here we have a distance between the electrode and the tank. So we know D. We know what is the cross-section, since we are looking for the height, and we know what is the material. So we have a capacity C1 given by the capacity of this part that is filled with the liquid. The capacity C2 is typically air. So here we have relative permittivity of 1. And again, this is changing as the liquid level is changing. So when the liquid level is increasing, C1 is increasing and C2 is decreasing. This works if the liquid that we measure has a significantly different permittivity than air, for example. So air has relative permittivity of roughly 1, well, almost accurately. And this could be, for example, water, which has relative permittivity of about 80 for, say, 20 centigrades. This arrangement works for non-conductive liquid. The problem with conductive liquids is that if you fill it in such a tank, the liquid is conductive and will short circuit the electrodes together. So you will not be able to measure capacity. So for non-conductive liquids, you need to insulate at least one electrode. So that's what you see here. The middle electrode is insulated, and we are again looking for the changes of capacity C1 and capacity C2. Water is slightly conductive, so for water it's the best to use already an insulated version like this. So we have one electrode that is insulated and the other is not. So again, here the one electrode is the tank and the middle electrode is installed into the tank. For circular capacitors, the equation for capacity is a little bit more complicated, but it follows the same structure. The capacity depends on the material, here epsilon 0 times epsilon r. It depends on the height and depends on the distance between the electrodes. You see that it's a linear dependence since all this is constant and this is changing with what we want. So the steady state characteristic of this capacity flow meter will be a linear function. and you may have a constant section which is given by the constant capacity plus then the linear section. So this is the best case that we can have. It is similar for the planar electrodes. So here is a normal capacitor. We have an electrode B times H, a plate, and we can again submerge it in the tank. We can look for capacity changes. This is a version for non-conductive liquid. If the liquid is conductive, you need to insulate the electrode because this would be a short circuit in the liquid. Here are a few examples of such sensors. This is a sensor for gasoline in a tank of a car, for example. So here you see it's this tube which you see here is hollow, and the liquid can enter through those small holes inside of the assembly. So it's filling a column here, and we are able to measure the capacity changes. So it's safe, it does not require any maintenance, and the electronics is either embedded here in this cover or you have it externally connected. Some more examples with wrought electrodes. So here you see 2 electrodes, for example, submerged into the tank, and we are looking for capacity changes. So what can we expect from this? This is suitable for applications that are aggressive. You can make the rod from corrosion-resistant material like stainless steel, for example, or titanium. You can build the sensor in such a way that it's not sensitive to build up on the electrodes. So the material can stick on the electrode, but it will not be a problem. We can have the silo directly as one electrode. So the silo has to be conductive. If it's metal, then it's fine. It cannot be plastic. And the second electrode is a rod or rope that you install into the tank. It can work with high temperatures up to 400 centigrades, relatively high pressures up to 100 bar. So I think, let me just look, how much do we have? Radar, yeah. So we have 2 more continuous sensors, and then we'll finish the talk with point level detection. I recommend you to take a look on those videos. Are quite interesting. You see applications and again explanation of the principles of this sensor. So we have basically seen this ultrasonic sensor already. Now this is used as a liquid level meter, but we have seen this already for position sensor. It's exactly the same. We have a transmitter, and this transmitter transmits an ultrasonic pulse. This pulse gets reflected from the interface, and it's reflected to a receiver. What you see here is the time delay between the transmitted signal and the received echo, and we are looking for the time difference. This time difference is proportional to the distance between the sensor and the interface, and also to the speed of sound in the particular environment, but we assume that this is a constant value, or we can measure the temperature. So if the liquid level is changing here, if it is getting smaller, then the distance between the sensor and the interface is getting larger, and we can measure what is the liquid level in the tank. So this is the answer for the question in the test. We're not looking for amplitude, but we are looking for the time delay between the transmitted and received signal. The ultrasonic liquid level meter may have problems with foam. So if there is foam on top of this interface, then this foam will absorb the ultrasound, and you will not see the reflection. So applications with foams. Few examples. This is the sensor. It's always installed from the top. We'll have we'll see the sensor also in the lab. The range is few meters typically, and the basic parameter is the shape of this cone. How do you transmit the signal? In what tank you can install it? A very similar, well, we can expect that this sensor will work with applications with about few bars, 4 bars, up to 150 centigrades. It is not affected by dielectric constant, as will be the case of radar, by density or moisture. It's quite important because the dielectric constant may be a problem for a radar sensor when it's too close to the dielectric constant of air. And it may be a problem, for example, for products like petroleum products, which have typically low dielectric constants. Moisture and density, okay, that's not such a big issue, but the density will change with temperature, so we need to measure temperature as well. What can be the problem here for ultrasonic is dust. So you can use it also for solids, but if you have a lot of dust inside of the silo, then the ultrasound may be absorbed by the dust, and you will not have a clear echo. Now, the last sensor for continuous reading will be a radar liquid level meter. It can operate based on 2 principles. One is the time of flight method, which you see here. So we are again looking for the time difference between the transmitted signal and received signal. The problem here is that the signal travels with the speed of light. So the distance that you measure, this is C0, speed of light. This time is what you measure, time difference. And here you see this is permittivity and permeability, so the properties of this liquid. So if this is very close to air, which has a relative permittivity and permeability of 1, then you may not use this radar sensor because it will not get any reflection. Here you are again looking for the interface. The second problem is that this time is very short, because the signal is traveling with speed of light, and radio waves travel with this speed, and it's about 300 meters per microsecond, roughly. So if you want to measure a short distance, then your time accuracy needs to be very high, in order of some femtoseconds, for example. So this time of flight method is suitable for larger distances, and the more common method that is used for smaller distances is called frequency modulated continuous wave. We have discussed this already for position sensors, so I will not go into the details, but you need a different arrangement of the sensor. You are transmitting a variable continuous wave, and you're not looking for the reflection as a function of time, but for the frequency difference, which is easily detected. Now this is how the radar sensor looks like. This horn is the antenna, so this is the only part that is in contact with the environment, so it can be also good for aggressive materials. The antenna can be made from stainless steel, for example, and then this is the electronic circuit that sends and receives the signal. The frequencies are in order of gigahertz, so typically either 6 gigahertz or 26 gigahertz 26 gigahertz is the industrial science medical band that where you don't need the license. The accuracy of this sensor depends on the bandwidth and only on the bandwidth. So, for example, if you change the frequency between, let's say, 24 and 26 gigahertz, then you have a 2 gigahertz bandwidth, and this will give you an accuracy of a few centimeters, for example. If you are increasing the bandwidth, then the accuracy gets better. So some industrial liquid level sensors, they operate at around 80 gigahertz frequencies, and you have roughly 3 times higher range accuracy. The accuracy can be under 1 millimeter, so it's quite accurate, but it's also quite expensive. To give you an idea, we are currently looking to acquire one of those radar sensors for our labs, and the price is about 250,000 Czech crowns, roughly. So it's very expensive. The ultrasound, on the other hand, will be something like 10,000. So the radar is really accurate, but really, really expensive. It is not affected by vapors or dust. But what can affect it is the eventual barriers in the tanks. You may have a tank, you may have barriers that reinforce the tank, you may have mixers, and from all this you may get reflections. So this may be a problem not for the radar and for the ultrasonic sensor as well. If you combine a radar liquid level meter together with a capacitive sensor, you may look for an interface between oil and water, for example, and you may also eliminate the problem with foams. So one of the videos that I recommend you to take a look shows exactly this. How is it possible to combine a radar with a capacitive sensor and fuse the two sensors together and have interface and liquid level at the same time. Okay. And the last point, it will be point level measurement. So point level measurement is very similar to proximity sensing. It gives you only yes or no answer. So yes, the liquid level is above a certain level or it is below, nothing between. So you can look for a full tank, you can look for an empty tank, for example, and that's it. We'll discuss only 2 possibilities how to do this. We can look for conductivity of the liquid. What you see here on the left picture is a continuous sensor. So you submerge 2 electrodes into the tank and you measure the conductivity between those 2 electrodes. This works only for conductive liquids, of course. So there is a current flowing between the electrodes, and this current is proportional to conductivity. So the conductivity sensor can be continuous, but can be point level as well. If it's a point level, it is arranged like this on the right picture. You have one electrode that is completely submerged to one pair of electrodes, and then you have one pair of electrodes here. It is outside of the tank. Now, here, this will act as a lower limit switch. So if the liquid level is above, you have a current and you know that the tank is not empty. And here, if the liquid level will rise above these electrodes, it will connect them together and you have current and you know that the liquid level is at least at this point. So you can install 2 or 3 point level sensors in the tank, and this allows you to get an info about the empty or full tank. This type of arrangement requires a conductive liquid, that's clear. So it will work with water. Now water is slightly conductive unless it's a distilled water, and therefore you can use it for water as well. Here you see an arrangement with 3 electrodes, so one electrode will go all the way down. So this will be common for the rest. Here I have one electrode here, one electrode there, So I will be able to detect one liquid level here and a second liquid level here. This works for temperatures up to about 150 centigrades, pressures roughly 25 bars. Some more examples. Here you see that the electrodes are either outside, there are 3 of them or 4 of them, like or 4 here, or there can be hidden inside of this tube for mechanical protection. And the last sensor will be a vibrating fork sensor. This sensor is suitable for liquids and solids. All the other sensors were suitable for liquids only. So how does it work? We have a mechanical part, a fork, that is submerged into the liquid. We make it vibrate with an exciter, which is typically a piezoelectric exciter, and we are detecting the motion. So in some way it is similar to this Coriolis flow meter. We make it vibrate and we are looking for the response. What will happen here is that the resonance frequency of this vibration will change if the fork is submerged or if it's not. And you are looking for this transition, for this change in resonance frequency. So this is a typical arrangement. Here you have a resonance circuit, a mechanical resonance circuit, so you make it move, and this tip is submerged in the liquid or in the solid, and we are looking for the change in resonance frequency or the change of the vibrations will stop completely if it's a solid material, for example. Now let's take a look on the video where we'll see how this works in an animation. Let me see. So the last video.
The most varied media are filled into and drained from storage tanks every day. Examples are potable water, fruit juices, oils and fuels, acids, brines, or even solids like grain, plastic pellets, or powder. Since these media can have completely different properties, there are different measuring principles to detect them. For example, point level measurement in liquids or bulk solids according to the vibronic principle, called also tuning fork principle. The tuning fork, which John Shore designed more than 300 years ago, served as a basis for the vibronic principle invented by Endresen Hauser in 1967. This principle uses the direct correlation between oscillation and damping in media. Let's have a closer look at how this measuring method works. Vibronic instruments monitor point levels in tanks, containers, and pipes. A sensor, in form of a tuning fork, is excited to its resonance frequency. The vibronic measuring principle in liquids is based on the resonance shift of a piezoelectrically excited oscillation system. There are 2 different piezoelectric drives, the bimorph drive in standard instruments and the stack drive in coated instruments. The bimorph drive consists of 2 discs, a piezo and a ceramic disc, which are connected to each other. At the same voltage, the piezos are compressed and the ceramic disc is bent. At different voltages, the piezos expand again. This causes the oscillations of the fork. The stack drive, however, stacks and fixes several piezo discs with changing polarization on top of each other. The application of a respective alternating voltage also causes the piezos to oscillate. As the piezos expand, the membrane
apart. As the piezo contracts again, the membrane is bent to the inside. The ends of the tuning forks, attached to it, are pulled together. As the tines of the fork are covered in a tank as the liquid rises, the resonance frequency of the tuning fork changes. The immersion into the liquid reduces the frequency. This frequency change is analyzed and converted into a switching signal. In solids measurement, only the piezoelectric stack drive is used. As the bulk solids cover the fork, the oscillation is damped. This changes the amplitude of the oscillation. The change is analyzed and converted into a switching signal. The vibronic measuring principle of Anderson-Hauser enables the point-level detection unaffected by the physical properties of the medium. For example, conductivity, dielectric constant, density changes, pressure or temperature. Turbulences, the formation of foam, or bubbling liquids do not impair the point-level detection either. We have an appropriate solution for any application.
Okay, so let's take a look on the properties of this sensor. So as we have seen, it's suitable for liquids and solids. We have seen the principle inside. So this is the tuning fork itself. This is the membrane, and here is the piezoelectric stack. It makes the fork vibrate, and when you submerge it into the liquid or in the solid, you are changing the resonance frequency. So here are a few examples of those sensors. So those sensors are for solids. They have a longer fork, and here is the piezoelectric stack. You can also have it like extended on a kind of chain, and this is then placed into the silo and detects the summit of the material if the silo is full. So the vibronic sensor is only point level, so it does not give you a continuous information. It's only yes or no, tank is full, tank is empty. It is not affected by foams or bubbles. It can work also as a detector for solids underwater. So if you have a mixture of water and sand, for example, as is typical for water treatment industry, then you may detect sediments on the bottom of the tank and clean it from time to time. It is for all pumpable liquids up to this high viscosity, and we don't have trouble with turbulence, with foam, and with bubbles. Questions? No questions? Great. So we have about 10 minutes to do the last Moodle test. So I will launch the last test.